In this video, we're going to discuss radicals and rational exponents. So let's begin with the radical. So we have a radical sign. So that's this symbol right here. And in this little position right here, there's sometimes a number there, sometimes it's blank. Whether it's blank or there's a number, that's called the index. And then the value on the inside of the radical symbol is called the radicand. Now, the index, like I said, it can be blank. When it's blank, that's a square root. If it's anything other than a square root, we need to put that number in there. This would be considered a cubed root. And then we'd have a fourth root. And we can have whatever number we want inside that index. But when it's blank, it's called a square root. And a square root is an even number. Square root. Cubed root would be an odd number. The fourth root would be an even number. So a square root is an even root. A cubed root is an odd root. And a fourth root is an even root. So if the index is even, it's an even root. And if the index is odd, it's an odd root. Now, if the index is even and the radicand is positive, then it's going to simplify to be real and positive. For instance, if we have the square root of 25, that's going to equal 5. The index is even, the radicand is positive, it's going to simplify to be a positive number that's real. Here's another example. If we've got the fourth root of 16, the fourth root of 16, the fourth root is an even index. 16 is positive. So an even index with a positive radicand is going to simplify to be a real and positive number. And that value is going to be 2. And let me show you why. 2 goes into 16 8 times. 2 goes into 8 4 times. 2 goes into 4 2 times. Because it's a fourth root, we'd be looking for groups of 4. There's one group of 4 2s. So that 2 goes to the outside. There's nothing left over, which means it's perfect. No radical left over. We could even look at the sixth root of 729. And the sixth root of 729, 3 goes into 729 243 times. 3 goes into 243 81 times. 3 goes into 81 27 times. 3 goes into 27 9 times. And 3 goes into 9 3 times. Because it's a sixth root, I'd be looking for a group of 6 values that match. That would be 6 3s. So one of those goes to the outside. There's nothing left over, so there's no radical left over, which means the sixth root of 729 is a perfect value, and it's 3. Positive radicand with an even index gives you a real and positive simplification. If we have the square root of a negative value, let's say -1, the square root, that would be an even index of a negative radicand, that's an imaginary number. So notice how it doesn't simplify to be real and positive. We're going to be working with real and positive values in this lesson. So this is the last time that we're going to see an I. I'm just going to confirm that. This is indeed the last time we will see an I in this lesson. Okay. Now, if the index is odd, So let's talk about when the index is odd. A cubed root, a fifth root, a seventh root. If the index is odd, then it simplifies to be real and it takes the sign of the radicand. So if the radicand is positive, your simplified answer is positive. If the radicand is negative, your simplified answer is negative. Example, we've got the cubed root of -8. The cubed root of -8, odd index, so a negative radicand is allowed. So we're going to have the cubed root of 8 is 2, take the sign of that radicand, and we get -2. And that's because -2 times itself 3 times is -8. So I'm just going to put because right here. Then we've got the cubed root of -243. So sorry, the cubed root of -343. Cubed root of -343 is equal to 7 with a negative, so that you get a negative times itself 3 times. That gives you that -343. And now let's do that fifth root of 243. The fifth root of 243, that's going to be a +3, and a positive because the radicand is positive, and because a positive times itself 5 times will get you back to that +3. So let's try and evaluate these two. So now that I've done some examples for you, evaluate this one and this one, these two tries. Press pause, and then when you're ready to check your answer, press play and come on back. Okay, the square root of 64 is 8, and the cubed root of -125 is -5. Okay, now we have the square root of 25 over 121. That's the same thing as the square root of 25 over the square root of 121. The square root of 25 is 5, and the square root of 121 is 11. So the square root of 25 over 121 is 5/11. Now the fourth root of 16, you might remember I've seen this one before and saying, well, the fourth root of 16, what times itself? 4 times is 16, and that's a 2. And this is where the exponent quizzes are really going to come in handy, because you should be able to recognize some of these numbers and be able to figure out the answer without having to break things down like I did up here. So 729 is a very special number. 16 is a special number. 343 is a special number. Those will be all over these lessons in this next unit. Okay, example, now we've got the square root of 4x squared. So now we've got this variable in here. So the only way we could take a square root of a 4x squared is if 4x squared is positive. Okay, so that's going to equal the square root of 4 is 2, and the square root of x squared is x. We can also think what times itself is 4x squared, and that's 2x times 2x. Now you might see that right there. And those bars are absolute value bars. And what they are is they're saying, I'm going to go back up here to the definition. If the index is even and the radicand is positive, then it's going to simplify to be real and positive. So it's simplified to be real and positive, +5, +2, +3. So if we want 2x to be positive, the only way to make that happen is if x is positive. So they on answer keys may put the absolute value around those x's. The cubed root of 8y to the 12th. Now remember, on an odd index, it's okay for the radicand to be negative. So we say what times itself 3 times is 8y to the 12th. I'm going to break this down for us. 8 is 2 times 2 times 2. And then y to the 12th, I've got 12 of those. That's 6. That's 9. And that's 12. So I'm looking for groups of 3. I have a group of 3 2s, which we knew the cubed root of 8 is 2. And then we've got a group of 3 y's, 3 y's, 3 y's, 3 y's. So I've got 4 groups of 3 y's. So that would be y to the 4th power. That would be y times y times y times y, which is y to the 4th. So our answer is 2y to the 4th. Okay, here we have a negative on the outside, a negative square root of x minus 4 to the 8th power. So I just put a little 2 in there to say I'm looking for groups of 2. Groups of 2. So I'd have x minus 4 8 times. So how many pairs would I have in those 8 groups of 8 binomials of x minus 4? Well, I would have 4 pairs. And you can say 2 goes into 8 4 times. So you can think, well, if I've got 8 of them, I'm going to have in pairs 4 pairs. So this is going to simplify to be x minus 4 to the 4th power. But this negative on the outside is going to stay. So my answer is the opposite of x minus 4 to the 4th power. Okay, let's try another one of those. Here we have the 5th root of negative 32n to the 10th. This is an odd index, so negative radicands are allowed. So the 5th root of negative 32 is going to be negative 2, because negative 2 to the 5th power is negative 32. And then how many groups of 5 n's would I have? Well, if I've got 10 altogether, I can group them into 2 groups of 5. 2 groups of 5. So that would be n to the 2nd power. So 5 goes into 10 twice. 5 goes into 10 twice. And I'll tell you why we're going into the exponent. We're not saying 5 goes into 32. We're saying 5 goes into 10 because 10 is an exponent. So n, 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 n. That's 5 of them. And then here's another 5. And that would make 10 n's. I would have 1, 2 groups of 5. Take 1 from each group, multiply them together, and that's how you're going to get n squared. Okay, you try the next 2. You could probably try the next 4 if you really wanted to. Okay, welcome back. If you tried the next 4, you would have gotten the square root of x to the 6th is x cubed. And if you need to, you can put a little 2 here and say I'm looking for groups of 2. And if you can expand it to be 6x's, so you'd have the square root of 6x's. So we're looking for groups of 2. That tells us groups of 2. So 2x's, 2x's, 2x's. I have 3 groups of 2. Take 1 from each group, and that's your answer. The next one, this would be n to the 4th power. The next one would be x minus y to the 3rd power. If I've got 15 binomials all together, then I'd be able to have 3 groups of 5. And here, if I have 8 m plus 3's, I'll be able to have 2 groups of 4. So that's going to give us m plus 3 squared. Okay, in the next video, we'll talk about the definition of the nth root of b, how we can write fractional exponents as radicals, and radicals as fractional exponents.